The ground beneath you is moving. Right now. 3 centimeters every year, the two shores of this strait are pulling apart from each other. Slowly, silently, relentlessly. The seabed below is soft as river mud, with no bedrock for hundreds of meters down. And in a region where the earth shakes harder than almost anywhere else in Europe, where fault lines run beneath the water like cracks in old porcelain, someone looked at all of this and decided to build a bridge. Welcome back to the channel. Today we are going deep, deeper than the water, deeper than the foundations, deeper than the cables and the concrete, into one of the most extraordinary feats of structural engineering ever completed on this continent, the Charilaos Trikoupis Bridge, connecting Rion and Antirion across the Gulf of Corinth in Greece. A bridge that should not exist, a bridge that the laws of conventional engineering said could not exist. And yet, it does. This is not just a bridge. Let that sink in for a moment. When most people hear the word bridge, they picture a structure anchored in solid ground, piles driven into bedrock, foundations gripping the earth like roots of a tree. This is not that. This is a structure built over 65 meters of open seawater on a seabed of soft alluvial sediment that offers almost no load-bearing grip, across a geological rift that is actively pulling the two shores apart at approximately 3 centimeters per year, in a seismic zone where a magnitude 7.0 earthquake is not a theoretical risk. It is a design requirement. Engineers did not ask, what if an earthquake happens here? They asked, when the earthquake happens, how does the bridge survive it? That question, and the answer they invented, is what more and more than equal of programs of the bridge from know. The gerential mention was fitter arraigns an even of riching city, that mentioned they don't really know with another worked of Christ the purchase predictively. That question, and the answer they just three. That question is what of the bridge survive it in a sort of the bridge in the change of the crip. That question is what more and more than no load-bearing grip is the ultimate love to enter their show. That question is what no load-bearing grip is experience. That question is what are the earthquake happens here, and the answer they just three. That question is what if the earthquake sinkle change anywhere whether China spirit from me, with a geological rift in the change of the crip. That question, as this consider they change no bridge from me in a dumption 50,000 year. That question is what if the bridge survived an atomatically structured bridge to do that minute. That question is what if the earthquake department with they invented is what this video is about. Imagine every nightmare scenario an engineer could face, stacked one on top of the other. The water depth, up to 65 meters at the crossing point, deep enough to swallow a 20-story building. The soil beneath that water, soft, weak, layered deposits of alluvial sediment that shift and compress and amplify seismic shaking rather than absorbing it. The seismic environment, one of the most geologically active regions in all of Europe, where the African tectonic plate and the Eurasian plate interact along a complex system of faults, generating earthquakes with terrifying regularity throughout recorded history. The tectonic drift. The two coasts are not standing still. The Gulf of Corinth is a rift, a zone where the Earth's crust is being stretched and pulled apart, meaning the ground on the Rion side and the ground on the Antirion side are moving in opposite directions every single year. The weather and sea conditions. Strong currents running through the strait, Mediterranean storms capable of battering construction equipment for days at a time, summer heat radiating off open water with no shade, and winter conditions that made precision offshore work genuinely dangerous. Each of those challenges alone would make a bridge project extraordinarily complex and expensive. Together, simultaneously, they made engineers across the world look at this strait and quietly conclude, not here, not yet, maybe not ever. And they decided to build it anyway. Before we continue, if you are new to this channel, please subscribe. We go inside the world's most extreme engineering projects, and we do not skip the hard parts. And stay with us until the very end of this video, because what the engineers invented beneath the surface of this water, in the dark and the pressure and the soft sediment of the Gulf of Corinth, had never been done anywhere on Earth before. The innovation is not just impressive, it is the reason bridges in earthquake zones around the world are designed differently today. At first, there was only the strait. No pylons, no cables, no road surface suspended in the air. Just open water, shifting tides, a treacherous seabed, and two small Greek towns. Rion, just north of the city of Patras on the Peloponnese side, and Antirion on the mainland side, connected to each other only by ferry, as they had been for generations. The idea of a fixed crossing was not new. The Greek statesman Charilaos Trikoupis, after whom the bridge is now named, had proposed the idea as far back as the 1880s. He stood in the Greek parliament and argued that a bridge across this strait was not a luxury but a necessity, a connection that would bind the Greek mainland to the Peloponnese and transform commerce, movement, and national unity. He was laughed at. The technology did not exist. The geology was considered impassable. The dream was shelved. It stayed shelved for over a century, not because people forgot, not because the idea lacked ambition, but because every generation of engineers that looked seriously at this crossing came back with the same answer. The ground is wrong. The water is too deep. The seismic risk is too high. The conventional tools of bridge engineering, pile foundations driven to bedrock, spread footings on stable soil, rigid connections between structure and ground, simply did not apply here. There was no playbook for this location. If you drove conventional piles into the seabed, you would find no bedrock to anchor into. The piles would terminate in soft soil, and under seismic loading, that soft soil would compress, shift, and potentially liquefy, causing the pile tips to lose their bearing capacity at exactly the moment when the structure needed it most. If you tried to build traditional spread footings on the soft seabed, the soil beneath them would not carry the enormous concentrated loads of a major bridge pylon without settling, tilting, or failing during an earthquake. If you attempted to reach bedrock by going deeper, the cost and complexity of piling to that depth in 65 meters of open water would be staggering. And there was no guarantee bedrock was reachable at any practical depth. Every conventional solution hit the same wall. The soil beneath the Gulf of Corinth was not the kind of ground you could build a major long-span bridge on, not with any technology that had existed before. So the solution was not to find better ground. The solution was to design foundations that could work without it, and to rethink, fundamentally, what a bridge foundation is supposed to do. Construction officially began in 1998. The project was a public-private partnership, with Jafira SA as the concessionaire and Vinci Construction Grands Projets, then one of Europe's leading infrastructure construction firms, as the main contractor. The engineering design was led by Burj Michalian, and what his team produced was a system that had no direct precedent in the world of bridge engineering. From the very first day of construction, the challenge was physical and immediate and relentless. The first phase was understanding, in granular, exhaustive, painstaking detail, what lay beneath the water. Survey teams spent months on the strait. They lowered sediment coring equipment into the sea floor and pulled up column after column of material, analyzing each layer, its composition, its density, its strength under load, its behavior under dynamic shaking. They mapped the underwater topography across the entire crossing using sonar, building a three-dimensional picture of the seabed they would have to work on. They consulted geological records, seismic catalogs, historical earthquake data, everything that could tell them how this ground behaved when the Earth moved. They ran computer simulations modeling soil response to different earthquake scenarios, different frequency spectra, different durations of shaking. They studied how the soft sediment would amplify incoming seismic waves, how it would interact with the structures above it, how it would behave not just under a single large earthquake, but under repeated seismic events over decades. Every soil core mattered. Every bathymetric measurement mattered. Every line of seismic data mattered. Because everything that followed, every dimension of every component of this bridge, would be derived from what those surveys told them. What they found confirmed what everyone had feared, and then some. The soft sediment layer was deep, consistent, and offered no practical path to bedrock. The seismic hazard was real and severe. and the tectonic drift was measurable and ongoing. The two sides of the strait were indeed moving apart, and the bridge would have to accommodate that movement not just for the day it opened, but for a structure lifetime of a century or more. Then came the foundation work, and this is where the story of this bridge truly begins, because what the engineering team designed here had never been built before. For each of the four main pylons, the solution was a reinforced piled footing. A foundation system that does not try to find bedrock, because there is none, but instead modifies the soil itself. Here is how it worked. Beneath each pylon location, construction crews drove a dense field of steel pipe piles deep into the seabed sediment. Approximately 200 piles per foundation, each pile with a diameter of around 2 meters. These piles were not designed to reach a hard layer and transfer load into it the way conventional friction piles work in better ground. They were designed to act as reinforcing elements within the soil mass, densifying it, stiffening it, improving its overall bearing behavior, and distributing applied loads across a much larger volume of ground than any single foundation element could touch on its own. Think of it as turning a large block of weak soil into something that behaves more like a coherent, reinforced composite. Not rock, but something far more predictable and stable than unreinforced soft sediment under seismic loading. The process of driving those piles was an operation of extraordinary precision, conducted entirely in open water, at depths reaching 65 meters. Jack-up barges were positioned over the work zones and fixed in place against the currents. Cranes handled massive steel pipe sections. Hydraulic hammers drove each pile into the seabed with controlled force. Remotely operated vehicles monitored the process below the surface. Divers conducted inspections and connected instrumentation. Positioning systems tracked each pile location to ensure the dense grid pattern was maintained with precision. The components and systems deployed during this phase alone formed a staggering list. The steel pipe pile casings themselves, the hydraulic pile driving hammers, the underwater pile guide templates, the jack-up barge positioning systems, the ROV monitoring equipment, the surface positioning GPS stations, the pile integrity testing instruments, the underwater concrete tremie systems for later stages, the anti-scour gravel blanket laid across the seabed, the survey frames and reference markers, the pressure transducers embedded in the soil, and the real-time load monitoring sensors that would remain in the structure permanently. Once the piles were in place, a massive concrete footing was cast on top of them, resting on the seabed, connected to and supported by the piled mass below it. Each footing was a wide, heavy disc of reinforced concrete, designed not as a thin plate, but as a robust, three-dimensional structure capable of distributing forces in multiple directions. Wide enough to spread load, heavy enough to resist uplift, strong enough to act as the transition between the soft, complex ground below and the rigid concrete pylon rising above. But the foundation system had one more critical element, and this is the piece that most people have never heard of, even people who have crossed this bridge dozens of times. Between the top of each concrete footing and the base of the pylon above it, the engineers installed friction pendulum seismic isolators. These are specialized bearing devices, mechanical systems built into the interface between the pylon and its foundation that allow horizontal movement between the two during an earthquake. When the ground shakes, the pylon does not lock rigidly to its footing and transmit every destructive force straight up into the structure. Instead, the isolators allow the pylon base to slide and rock, absorbing energy, dissipating force, decoupling the violent motion of the ground from the structure above. The pylon moves, the bridge moves, but in a controlled, engineered way. Not in the chaotic, catastrophic way of a structure fighting forces it cannot manage. Without the isolators, a major earthquake could concentrate stresses at the base of each pylon until the concrete cracked, the reinforcement yielded, and the pylon failed. With the isolators, the earthquake energy finds an engineered path, a movement that is permitted, predicted, and safe. This was not a small refinement. This was a paradigm shift in how bridge foundations in seismic zones are designed. Then came the pylons themselves. 4 towers of reinforced concrete rising from the sea surface to approximately 230 meters above sea level. Building towers of this height on land is a substantial engineering challenge. building them from platforms over open seawater, managing access, supply chains, working at height in wind and weather, maintaining precision over hundreds of meters of vertical construction, is an entirely different magnitude of difficulty. The pylons were built using slip forming, a continuous casting method where the concrete formwork advances upward as each lift of concrete is placed, cured, and gains strength. This technique allows the towers to rise without interruption, without the stop-start cycle of conventional staged forming, maintaining consistent concrete quality and minimizing the number of construction joints in the structure. The concrete mix used had to meet strict requirements for strength, workability, and durability in the marine environment. Resistant to chloride penetration, resistant to carbonation, designed to protect the steel reinforcement inside it for the full design life of the structure. The shape of the pylons was not chosen arbitrarily. They flare outward toward their base, widening as they approach the bridge deck. This form serves a structural purpose. The wider base increases the contact area and load distribution at the deck connection, reduces stress concentrations, and improves the stability of the pylon under the combined vertical and lateral forces generated by the cable stays above and the seismic and wind loads acting on the full height of the structure. Form and function are inseparable here. Every geometric decision carries a structural justification. Every pour of concrete mattered. Every surveying check of the pylon's verticality mattered. Every lift of the slip form mattered. Because any deviation from the design geometry would propagate upward through every subsequent meter of the tower. And errors at the base of a 230-meter pylon become significant errors at the top. Then came the cables and the deck, the visible skeleton of the crossing. The Rion and Antirion Bridge is a cable-stayed structure, with cables radiating from each pylon in a fan arrangement to support the bridge deck below. The four main spans between pylons measure 560 meters each, a span length that places this bridge among the longest multi-span cable-stayed bridges built up to its time. The deck was constructed in segments, fabricated partially on shore and partially assembled using floating cranes and barges, then lifted into position and connected span by span as the deck grew outward from each pylon. The cables themselves are bundles of high-strength steel strands, each strand drawn to precise dimensions and tensile strength specifications, each bundle wrapped in a protective polyethylene sheath to resist the corrosive combination of salt air, humidity, and ultraviolet radiation in the Mediterranean environment. The total length of all cable strands combined runs to roughly 500 kilometers of steel, an almost incomprehensible amount of precisely engineered material woven into the load-bearing skeleton of this bridge. Installing each cable required threading the strands through their anchors at both the pylon and the deck, tensioning them to exact loads, and verifying that the tension was correct before moving on. The tensions in the cables are not arbitrary. They are precisely calculated to produce the correct deck geometry, the correct load distribution through the pylons, and the correct stress state in every element of the structure. Adjusting one cable changes the forces in every other cable connected to the same pylon. The calibration process was iterative, careful, and took months to complete correctly. Beneath and within the bridge deck, running the full 2,880-meter length of the crossing, are systems that the driving public will never see and almost never think about. The deck contains the main longitudinal box girder structure, the transverse deck beams, the reinforced concrete road surface, the waterproofing membrane, the drainage channels and outlet pipes, the expansion joints, specially designed for large seismic displacements, far beyond what a standard highway joint is built to accommodate. The cable anchor blocks embedded in the deck concrete, the maintenance access catwalks inside the box girder, the inspection trolley rail systems on the exterior, the full electrical conduit network for road lighting, the traffic monitoring camera systems, the wind speed and direction monitoring stations at multiple points along the deck, the seismic accelerometer network continuously measuring the bridge's dynamic response, the cable monitoring sensors measuring tension changes in real time, the navigation lighting systems for marine traffic below, and the fire suppression systems in the enclosed sections of the deck structure. Every one of these systems was designed for the specific demands of this location: the seismic environment, the marine exposure, the long spans, and the fundamental requirement that the bridge must remain operational, or at minimum safe, immediately after a major earthquake. Not after weeks of repair, after the event itself. Then came the testing. Load tests with controlled weights placed precisely on the deck to verify deflection behavior matched the design models. Dynamic response tests using mechanical vibration sources to characterize the natural frequencies of the structure. Cable tension verification across all stays after the full deck was loaded. Seismic monitoring system calibration. Bearing inspection and certification. Expansion joint performance testing. And a full inspection regime. Visual, instrumental, and analytical, before any determination was made that the bridge was ready to open. The Rion and Antirion Bridge opened on August 12, 2004. The timing was deliberate and meaningful. The Athens Olympic Games were beginning, and Greece opened this bridge as a statement to the watching world. Not just a statement of infrastructure, a statement of what Greek engineering ambition, combined with the best of international construction expertise, could achieve in a place where everyone had once said, "It cannot be done." In 2006, the International Association for Bridge and Structural Engineering recognized the bridge with its Outstanding Structure Award, the highest recognition in the global structural engineering community. Most drivers who cross this bridge today experience it as a smooth, unremarkable few minutes over blue water. They see the pylons rising against the Greek sky. They notice, perhaps, the cables fanning out above them. They feel the slight flex of the deck. They arrive on the other side. They do not see the approximately 200 steel pipe piles packed into the seabed beneath each pylon. They do not see the friction pendulum isolators sitting between each pylon base and its footing, ready to absorb the next earthquake. They do not see the decades of tectonic movement already factored into every dimension and joint and connection of this structure. They do not see the real-time monitoring network, accelerometers, cable tension sensors, displacement meters, silently transmitting data every second of every day to engineers who are watching this bridge the way a doctor watches a patient. They do not see the 500 kilometers of steel cable strands holding the deck in the air. They do not see the seismic isolation philosophy that runs through every design decision, from the deepest pile in the seabed to the last expansion joint in the road surface. They do not see the century of waiting, the ferries, the proposals, the rejections, the engineers who said it was impossible, that preceded the 6 years of construction that made it real. This bridge is a record written in concrete, steel, and the refusal to accept impossibility. It is proof that when the ground gives you nothing to stand on, you can engineer your own ground. It is proof that the most hostile forces in nature, soft soil, deep water, active faults, tectonic drift, can be understood, modeled, and turned from threats into design parameters. It is proof that when human ambition, scientific rigor, and genuine engineering creativity work together, the answer to "can it be done" can be yes. Here, now. Watch. The Charilaos Trikoupis Bridge spans approximately 2,880 meters across one of Europe's most seismically active straits, standing on a foundation system built for soft seabed with no accessible bedrock, designed to survive a magnitude 7.0 earthquake through seismic isolation technology that had never been deployed at this scale before. Constructed between 1998 and 2004, and recognized in 2006 with the International Association for Bridge and Structural Engineering's Outstanding Structure Award. The two shores it connects are still moving apart, approximately 3 centimeters every year. And it works. If this video gave you something, subscribe to the channel. It genuinely helps us keep making these. Leave a comment below. What do you think is the single hardest engineering problem this bridge had to solve? The soft seabed? The seismic isolation? The tectonic drift? The water depth? I want to know what got you. Thank you for watching.